For a reaction, delta G naught is the standard free energy change if all substances in the reaction are at standard conditions. If we don't have standard conditions, the free energy change delta G is found using this equation. Delta G is equal to delta G naught plus RT log Q, where R is the gas constant, 8.314 joules per mole Kelvin. T is the absolute temperature, that is the Kelvin temperature, and Q is the reaction quotient, which is products raised to their powers over reactants raised to their powers. It has the same form as the equilibrium constant, which hopefully you're familiar with, but it's not at equilibrium. We note here in the picture that comparatively few reactions in industry take place under standard conditions, so it's imperative that we be able to calculate some things when the conditions aren't standard. Let's show this with an example. We're going to calculate delta G at 198 Kelvin given the following information. This is the Haber process, where nitrogen and hydrogen gases combine to form ammonia. There is an equilibrium that is set up between those, and at this particular instant we have certain pressures of those gases, and we're at 198 Kelvin. We note here first that 198 Kelvin is not standard temperature. Standard temperature is 25 degrees Celsius, which is 298 Kelvin. We're not at standard temperature, and standard pressure would be 1 atmosphere of pressure for all of the gaseous substances. And here we are not at standard pressure for 2 of them. You can see that the hydrogen is at a pressure of 3 atmospheres and the ammonia at a pressure of half an atmosphere. To calculate delta G, we're going to use the equation that we introduced on the previous slide. To use this, we first need to find delta G naught. Now this is fairly easy to find. We're going to go products minus reactants for the substances in the equation, and we need to look up these delta GF naught values. But before we do that, let's, I hate to use this word, think, are there any of them that we know without looking them up? And that would be yes. The nitrogen and the hydrogen are elements in their standard state, in their gaseous phases, so the delta GF naught value are 0. For any compound, of course, that value is not going to be 0, so we would definitely need to look up ammonia. Turns out to be negative 17 kilojoules per mole, and in the equation we have 2 moles of ammonia. Delta G naught is negative 34 kilojoules. What's Q? Q is products raised to their powers over reactants raised to their powers. You can see that we have 0.5 atmospheres raised to the second power because the coefficient in front of the ammonia is 2. In the denominator we have 1.0 atmospheres for the nitrogen, simply raised to the first power because the coefficient in front of the nitrogen is 1, and in front of the hydrogen is at a pressure of 3 atmospheres, and the coefficient in front of the hydrogen in the equation is a 3. And we get that number, 0.00926. Now we're ready to put the whole thing together. We want to make sure that our delta G naught is in joules, because as you recall, this value of R, which is 8.314, has the unit joules in it. Do not use kilojoules for this delta G naught value. So there it is. Negative 34,000 is the delta G naught term. Then we add in our R value, 8.314. We add in the term for temperature, which is in Kelvin, and then we take the natural log of Q. And you get your friendly calculator out, you type that in. I converted it into kilojoules because it's a smaller number, negative 41.7 kilojoules. In other words, this process, under these conditions, is thermodynamically favorable.